Okay, in this video I'm going to talk about the Fermat's theorem in mathematical analysis, and it's also known as the stationary point theorem and also as the interior extremum theorem. So basically, so let's state this theorem. So basically we have a function that is defined on some interval. So we have a function it's defined on some interval from a to b to real numbers, and if we have, so if it has a local extremum at point x0, so if x0 is a local extremum, so okay, if x0 in this interval ab is a local extremum of f, of the function f, then it is differentiable at this point x0, and f is differentiable at x0, then it follows that the derivative at this point x0 is equal to 0. So it is important to notice that, to notice how little we assume. So the function doesn't have to be differentiable everywhere on the interval from a to b. It has to be differentiable only at one point, at this extremum point, at x0. And the function doesn't even have to be continuous on the interval ab. So we really assume very little about the function. The only two assumption is that at x0 this is a local extremum, so it means that there is some interval for some delta. There is some interval that small interval around x0 such that f of x0 is the maximum, either maximum or minimum on this interval, and it is differentiable only at x0. That's all we assume. And it is important also that x0 is the interior point. So this name of the theorem, alternative name, interior extremum theorem, this word actually captures this condition. So it is very important that x0 is an interior point. So the function has to be defined from both sides of x0, on the left and on the right. So it cannot be, for example, if we have a function that is defined only a function from closed interval from a to b, and we have an extremum at one of the boundary points, for example at a, then this theorem wouldn't work. So it has to be defined from both sides of x0. So that's an important condition. But other than that, so that's the only basically two conditions that we assume. The function can be anything. It doesn't have to be continuous on the whole interval. It doesn't have to be differentiable. Okay, so let's prove. So first write formally the condition that x0 is a local extremum. So this condition is a local extremum. So formally it means that there exists such number delta greater than 0, such that f of x0 is the maximum like either maximum or minimum is okay. Let's write is either the maximum or the minimum on the interval, like the maximum or the minimum value on the interval x0 minus delta, x0 plus delta, and it has to be defined on this interval. So that's where we use that x0 is an internal point. Okay, so that's basically we wrote the condition that it is a local extremum. So this condition. And now the fact that it is differentiable yeah, so by definition, the derivative is defined as a limit. So f, so the derivative of x0 is defined as the limit let's say of h tends to 0. Tends to 0 of the f of x plus h, x0 plus h minus f of x over h. Yeah, so that's the definition of the derivative. And now since it exists, so since the function is differentiable, it is also equal to the right hand derivative and the left hand derivative. So the derivative, so like there is a definition of left hand derivative x0 minus, it's the same limit only when h tends to 0 from above. So from below, this is the left hand derivative. So this kind of, we can write it as minus 0. So h is always, so this means that h is always less than equal than 0. So we take the limit when h is always less than equal than 0 of the same expression. So f of x0, so here it's also x0. Plus h minus f of x0 and also the right hand derivative the limit of limit when h tends to 0 from above, so when h is always greater or equal than 0, of x0 plus h minus f x0 over h. So since the full derivative exists, then it must be equal to both the right-hand derivative and the left-hand derivative. So f, the derivative of f at x0 is equal to f prime, so the derivative at x0 plus and is equal to the derivative of x0 minus. So if the limit exists when h is tends to 0, like from any side, when h can be any number, then both of these limits exist when h tends to plus 0 and to minus 0. So but we notice that this expression, f of x0 plus h minus f of x0 over h. So let's evaluate this expression depending on where h is positive or negative in the within the delta interval. So when h, so let's write it this way. So when h belongs to the interval of 0 to delta, and when h belongs to the interval of minus delta 0. So when h is positive and less than delta, then this expression would be so the notice that, so let's assume that f of x0 is a local maximum. So the local minimum case would be considered similarly. So we write either, okay, so either the maximum or the minimum on this interval. So without loss of generality, so without loss of generality, we assume that it is the maximum, that f of x0 is the maximum on this interval, is the maximum on this interval from x0 to minus delta, x0 plus delta. So when it's a minimum, this case can be considered similarly. So since it's a maximum, so basically this is a maximum on this interval, and in particular it is greater than this, because x0 plus h still belongs to this interval when h is in these limits. So then so basically f of x0 is greater or equal than f of x0 plus h, right? Always. When h, so when h belongs to the interval minus delta. So therefore the numerator of this expression, of this fraction, is always less or equal than 0, right? because f of x0 is greater or equal. So this is less or equal than 0. The whole numerator is less or equal than 0. And the denominator, its sign depends on either h is positive or negative. So if h is positive, so in this interval, then the denominator is positive, the numerator is negative, therefore the whole fraction would be negative. So it's less than or equal than 0 in this case, and it's greater or equal than 0 in this case, right? Because in this case we have the numerator is still negative, but the denominator is also negative. Therefore, the whole fraction is positive. Positive or 0. Yeah. So that's how we evaluated the sign of this expression, depending on where h belongs. So now we see that, so now we return to the definition of when h approaches to 0 from below and from above. So when it approaches from below, so this expression, then h is always, so when h is less than delta, and it is also negative, so h belongs to this interval, therefore the whole expression under limit is greater or equal than 0. Therefore the whole limit would be greater or equal than 0. So this limit would be greater or equal than 0. On the other hand, when h approaches to 0 from above, so this limit, the right hand limit, the expression is, when h is less than delta, the expression under the limit would be less or equal than 0. Therefore, the whole limit would be less or equal than 0. Right? But on the other hand, we established that these two limits, right hand limit and left hand limit, are equal to each other. So one of them is greater or equal than 0, the other is less or equal than 0, but they're also equal to each other because they're equal to the full derivative of f at the point x0. So therefore, the only possibility is that they're both equal to 0. So from this it follows that, the f, the derivative of x0 minus is equal to the derivative of x0 plus and is equal to 0. So one of them is greater or equal than 0, the other is less or equal than 0, but they're also equal to each other, therefore they're both equal to 0, and they're both also, like we established, that they're both also equal to the full derivative. So the full derivative is also equal to this expression x0, and this is what we need to prove. So therefore f, the derivative f at x0 is equal to 0. And this concludes the proof of the theorem. But just once more to iterate that we used here that the function is defined on both sides. So to consider that both the right hand limit and the left hand limit, we use that x0 is an internal point in the interval. So the function has to be defined on both sides of x0. Yeah, so that's it for this video.